welcome everybody to this ACC Knowledge Series. We are happy that you could join us today, this morning. You had the choice of many webinars to attend, but you chose ours, and we are glad that you did. We promise to make this an enlightening and enjoyable session with you today. We have ACC as the main idea with ACC is that we have over the years since 1936 been promoters of innovation and research in the field of construction. We bring to you a strong focus on building better building practices, as well as supporting that through research, through sustainability practices, through good workmanship. And we hope that all of you as experts and experienced people will also be sharing that advocacy in your sites, in your projects. I have my colleague, Dr. Mahesh Tandon. He will be introducing our topic as well as Professor Nikhil going forward. Just before we start, my recommendation to you is when you do have questions, please do share your questions only and only in the Q&A section. This is so that we keep track of all of your questions and are able to take those questions either in the middle when we will try and take a break after we cover some of the sections that the professor has, or towards the end. And I do encourage you to go onto that Concrete Club app and try and leave some of your questions for that as well. With this, I encourage Professor Mahesh Tandon to please join us and introduce the speaker and the topic for today.
Thank you, Priyanka. On behalf of ACC Cement, I welcome you all, and I welcome Professor Narayanan Naithalet for this today's knowledge ACC webinar series. Professor Narayanan Naithalet is currently professor in structural engineering and materials in civil engineering department in Arizona State University. He obtained his PhD from Purdue University in the area of cement-based material. He has done his PhD, and he has been teaching and researching concrete material and system for the past almost 20 years. He has published more than 150 international journal papers and about 150 papers in conference proceedings in the area of development, characterization, performance testing, and modeling of cement-based material. He has been invited to deliver keynote talks on several aspects related to cement-based material, including microstructure and properties, materials modeling, concrete 3D printing, and durability. He is a recipient of several awards, including the Walter Huber Civil Engineering Research Prize of American Society of Civil Engineers. He is a fellow of American Concrete Institute. He is going to talk on today ultra high performance concrete and its application in building and infrastructure. What we will have, maybe after 30 minutes of the presentation, we will take up 1 or 2 questions. As Mrs. Priyanka mentioned, you can go and post your question in Q&A tab. We will try to address the questions from the session what is covered, and the end of the session also we'll take up the question. Over to you, Professor. Thank you, participants.
Thank you, Dr. Mahesh Tandon, and a very good morning to all of you in India, or whatever is the time, wherever you are in the world. I'm going to share my screen today. And okay. It's all clear, right, Mahesh Tandon? You can clearly see that, right?
It's clear, sir. You can go ahead.
Okay. So we're going to talk about ultra high performance concrete and its applications in building and infrastructure. So typically, when we talk about concrete in our regular everyday use, we talk about concretes that are 30 megapascals, 40 megapascals in strength. When you're talking about high strength concrete for special applications, you talk about 50, 70, 90 megapascal concretes. But there are cases where you would need extremely high strength, and we are talking about compressive strengths greater than 150 megapascals. the advantage of such high strengths, we will come to it as we go through in this presentation. But with higher compressive strengths will come higher tensile strengths also. But we know that concrete is inherently brittle in nature, and therefore when you have a higher compressive strength, the propensity is for the material to fail or crack suddenly, causing very sudden failures. So which you don't want, and therefore typically when you increase the strength, you need something along with it to improve the ductility, for which you will need fibers. So we are looking at let me just get my pointer up. So we're talking about using fibers of the order of 1 to 3% also when we are doing ultra high performance concretes. Somebody wants a single page slide. Let me see if I can do that.
It's okay, Professor. Now it's pointer is clear.
What's that?
Pointer is clear now. You can use the
No, is it somebody wants a single, just a single slide. Okay. Is this better?
Yeah, better. Clear.
Okay.
You can go on to the presentation mode.
Where do I go? That's what I did. I did my slideshow mode, but it's showing me other thing also. But that's okay. I'll just do this. It's clear to everybody, right?
Yeah, Professor. You try once again the presentation mode, Professor.
How about this?
That next slide, that portion is coming.
Yeah,
but
next
anyway,
slide.
This
is better. You please proceed.
Bottom over here. If you can go back to the previous view.
Okay.
And just below the slides, yes.
This one?
I believe
No, that gives you all the slides.
The third icon, the fourth icon, yes.
Now that's blocking or unblocking the slideshow, so that doesn't do anything. Oh, hide presenter screen.
Yes, hide presenter view.
It comes back to this. That's okay. We will do this. So you need higher amount of steel fibers to make sure that you increase the ductility of your concrete so that it doesn't fail suddenly. And then one of the important things that you need with ultra high performance concrete is that you need to pack. You can see here, you need to pack your microstructure so well. And I'll tell you why we need to do this as we go through. So a few key things: 50 to 100 megapascal for your traditional high strength concretes, 150 to 300 megapascal for your ultra high performance concretes. Okay, so the idea is you need a very high compressive strength, but then compressive strength is not the only criteria of importance for, oh, I think I know why this is happening. I have my full screen here. Is this better now?
Perfect.
Yeah, perfect. Please go ahead.
Yeah, now I figured it out. So high compressive strength is not the only criteria. Increasing the compressive strength alone does not lead to crack resistance, ductility, and durability. We know that compressive strength is an important characteristic of concrete, and everybody wants to use compressive strength as the key characteristic. But then you need other features in concrete also in order to give you the characteristics that you need. So you need overall performance. Compressive strength is one thing, but we need flexural strength, tensile strength, shear capacity. If you're looking at building multi-story structures, if you're looking at building bridges, you need high shear capacity, you need service life, you need all of those things. So we need to look at a complex of different things, and that is where the whole concept of ultra high performance concrete becomes important. So it's not just to get a high strength that you can get in whichever way you want. The idea is to make sure that you are getting a high performance from all different aspects. So I don't think you're seeing the next slide. Oops. Okay. So the advantages of UHPC are adequate control of shear cracking in conventional concretes, which require very tightly formed rebar cages. You might need a lot of rebar for very high load carrying structures, which increases the cost of structural member. But if I can make concrete take a lot of shear strength, you can reduce the amount of steel. With the enhanced tensile strength, you always have shear capacity that's improved. Tensile cracking is reduced. We know that cracking will ensure that, or reduced cracking will ensure that the structure is a lot more durable. And that's where fibers will come in with ductility and crack resistance. If you're a structural engineer and you're worried about development length and anchorage of steel reinforcement when you're connecting different members, extremely high strength of UHPC can actually reduce the development length of steel members. You can have a much more robust development length application. So here a few applications, a few pictures. This is Mars Hill Bridge in Iowa, one of the first UHPC bridges in the United States. Here is a Cat Point Creek Bridge in Virginia. They're all the accelerated bridge construction ideas where you can go in and construct a bridge pretty quickly. Ultra high performance concrete decks are used for extremely high performance. You can use it for overlays. And one of the most common applications is what you see on the bottom right here, where you're using UHPC for deck closures. This used to be done with steel, so steel deck connectors, but we know that steel has issues with corrosion. But now if you can get a concrete that can perform very similar to steel, now you don't have the incompatibility issues between the decks or the girder and the T-bulb and all of that, and you get a much better performance. So this has been one of the newer applications of UHPC. So a few more points along those lines. If you can design the material cheaper, you can reduce the life cycle cost because this material is going to be a lot more durable than your conventional concrete, which I'll show in a minute. Now, because this is very strong and you can build in ductility features, you can design and build a precast multi-story building with about 20 by 20 meter column-free base, which means you can get large open spaces because of the extremely high strength. You can use it for sunshades, cladding, roof components, all of those because they are all slender and durable. You can do it for geometrically complex architectural shapes. You can do it for bridges, which spans much longer than what we do now with precast pre-stressed concrete. You can use support structures for energy applications, blast-resistant facades for protection of military personnel, or protection of important buildings, repair and strengthening of infrastructure, repair and strengthening of nuclear containment structures. All of those are tremendous advantages that this material has, especially given the fact that in the US, we are talking about a lot of infrastructure repair now. A lot of buildings and bridges and nuclear power structures are ending the life or reaching the end of their service life, and you would need a lot of repair and maintenance. And this is one very special concrete that can play a big role in that. Sustainability, I just put it at the end. I know everybody wants to see it first and foremost. It's not because it's not important. I just put it at the end because there are still questions that we need to answer based on what we know about this material yet about its sustainability. But in general, because you can make the cross-section smaller because this concrete is very strong, you can have lower amounts of concrete. Lower amounts of concrete translates to lower amount of cement. So you can better control the cement consumption and increase the sustainability of such structures. Here are a few experimental tests that Federal Highway Administration, the US, have done. This is pie girders with UHPC. And I'm showing this now because towards the end, I'll show you some ideas that you can use structural design with these, very brief ideas of structural design with these pie girders. And you can see these pie girders being installed in a bridge in these pictures. Okay, field connections, which I talked about. You can have adjacent precast deck panels. If you have two different deck panels that have to be joined, which you see in the picture up. So this is one deck a panel, there's another deck panel. You have to join these two deck panels, which means this area will have to be filled with an extremely strong and tough material. Remember, this is a deck. These are two deck panels that are connecting, which means when vehicles go on top of it, you're going to have extreme amounts of fatigue here. So you don't want failure driven by loss of ductility, which is what fatigue does. And you would know that even a ductile material would behave brittle under fatigue behavior, so fatigue loading. So you want to make sure that this has quite a bit of toughness, and you will see, and also you know that the spacing is not that much. So you need a really flowable concrete that can go in and fill. So now we are coming into two conflicting requirements. You say that I need the concrete to flow, but I need the concrete to be very, very, very strong also. If you look at the history back, UHPC started off as what we call reactive powder concretes, where you have a very high amount of reactive powder, but then used very low amounts of water and quite a bit of compaction to get the reactive powder compacted in place to get the structure. But you cannot put in a very stiff mix and hope to compact in between here. You need it to be flowing. So now we need to think about a mix that will give you a lot of workability, plus be able to give you 150 megapascal strength, which means admixtures, different types of admixtures are required. And we'll talk about that. There are other applications, precast deck panels to girders, link slab connections above the interior supports of bridge structures, simple connections without requiring post tensioning, several different applications that people are looking at. So here are a couple of examples of feed connections. So you have a deck and then deck panels that are coming in, the waffle decks coming in here, and then the UHPC being poured in between as a connection, another connection between deck panels that you see here. So simplistic ideas as to how you would do this in the field. So let's talk about the material design. Let's talk about how we would create such a material. Now, very simply, about 20, 15 years ago, 10 years ago, if you would come and tell me, I need a very strong concrete, I would say, yeah, cement guys would be very happy. I'm going to put in a lot of cement in that concrete, and therefore I will get strength. But over the last 10, 15 years, our understanding of how we make concrete mixes have dramatically changed. And it's actually for the good, because sustainability was a big driver. We figured out that we cannot use the levels of cement that we have been using. 500, 600 kilograms of cement per meter cube of concrete is no more a possibility, but we still need the property. So how would we do it better? So a few things. You need to have a very low water to cement ratio, water binder ratio to obtain strength. That goes without saying. And you know, right from your first class in concrete, strength is inversely proportional to the water cement ratio. Therefore, you lower the water cement ratio, you get good strength. But then I showed you in the last picture, I need my concrete to flow very well also, which means that's another conflicting requirement. To make sure that that happens, I need to have a lot of admixtures. So now I need to add admixtures, but admixtures don't really work without a certain amount of water to make sure that they can be carried everywhere in the mix. And that is where we typically come to a number of about 0.2. 0.18 to 0.2. Beyond or below 0.1718 to 0.2, you will not get enough efficiency with the admixture also, and you may have to use tremendously high amounts of admixtures, which will increase the cost of your mixture, which also I will show you as we go through. So for self-compacting concretes, you need large admixture dosages. And then the other important question, and I'll show you that in a while. If I want very high strength, I can put in a lot of cement. But what's the whole point of putting in a lot of cement when my water cement ratio is only 0.2? That cement is not going to be hydrated. That cement is not going to have a chemical reaction to give it strength. Therefore, I need to figure out a different way where I need cement to hydrate as much as it can, but then a lot of other small particles to be around my cement grain so that a good bond is built completely, a good non-porous structure is built. And that is where this design takes a completely different turn. So I need a lot of different powders. Those powders should ensure particle packing. So I should have good packing of particles, and they should ensure my cement reacts good enough. So you need several types of fine powders, and we will talk about a few types of fine powders that we look at. There are several different varieties that you can try depending on what's available locally and what works for different cases. Now, every conventional ultra high performance concrete that you have, and since I'm talking at ACC today, Lafarge Holcim, Lafarge has ductile, which is the first commercial ultra high performance concrete mix. And all commercial ultra high performance concrete mixtures are basically ultra high performance mortars. Very, very rarely do you have aggregates in ultra high performance concrete, basically because you want very, very high strengths. That is number one. And also you want to make this flow in very tight spaces. Mortar is obviously a much better choice than concretes. But then there is always a problem if you compromise with aggregates. Number one, your cost is going to be high. Aggregate is a cheap filler that we all love in concrete because it's going to make concrete cheaper. And second, from a structural point of view, from a materials point of view, aggregates are much more stable than your cement paste. Your cement paste is susceptible to volume changes, shrinkage, cracking, all of those things. Your aggregates are much more stable volumetrically. Therefore, when you have a certain amount of aggregates, it lends a much better volumetric stability to your mixture. Therefore, you need to think about adding smaller aggregates. I'm not talking about 20 millimeter size aggregates, but I'm talking about smaller aggregates, and not 60 or 70% by volume of concrete. That will not give you your 150 megapascal strength. You need some amount of aggregates, small amount of aggregates, maybe 35, 40% by volume of your concrete to give you volumetric stability and to reduce the cost. So that is something that needs to be thought of. And that's one important thing as we go on developing these mixtures. People who are demanding this are asking, especially when you're doing deck surfaces and things like that. Okay, so let's look at a few materials. And I want to focus on a few things. So this is your particle size distribution. The solid line is a typical ordinary Portland cement. We call it C150, ASTM C150 cement here, which is very similar to your 43 grade cement, generally in terms of fineness. In the US, we really don't have a 53 grade cement. We really don't have grades of cement. We just have ASTM C150 cement. We have type 1, type 2, type 3. So your grade 53 is typically a type 3 high early strength cement, but this is not a high early strength cement. We're still using a normal type 1 cement. And then I have a lot of other materials. So I have slag, which is slightly finer than cement, fly ash, which is slightly coarser than cement. And then here I have metakaolin that's finer than cement, limestone that's finer than cement, silica fume that I have not shown here because it's even finer than cement. So you see here a variety of different fineness, a range of different fineness. And my idea is to make sure that I use these finenesses to fill my space in a most effective and efficient fashion. So this is basically about a space filling idea. So there is slag, metakaolin, limestone, fly ash. You can use, people use quartz powder if that's available, cheap. We chose to use limestone, and I'll tell you the reason for using limestone in a minute. So just to give you one more slide to look at what different particles are, and you can see here a series of different particles. Coarse aggregates large, sand, fine aggregates smaller, Portland cement, fly ash somewhere here. And as you go finer and finer, there is nano silica, there is precipitated silica, there is carbon nanotubes that people are using for ultra high performance concretes. But we try to keep it simple. We're not using too many different ingredients because anything that you go towards the left in this curve, you're going to make it much more expensive. So that is the idea. So a few particle types. Now, how do I pack all these particles? So here is a quick picture that shows you what happens in packing. This is a two-dimensional slice from a three-dimensional structure. So you can just look at it and see that This is the case for a cement only packing. If I add cement and fly ash, I get a little better packing. Cement, fly ash, fine limestone, which is in green color here, even better. With silica fume, even better. So from plain cement to cement, fly ash, limestone, silica fume, I've increased the overall packing, but also look at the number of red particles. I have been able to sequentially reduce the amount of red particles, right? So I've been able to sequentially reduce the amount of cement. So I've packed the structure much more. I have mixed all of these different things. I've packed it much more. But then with improved packing comes improved or higher demand for water. So that is another thing that we need to think about. So I'm just jumping on to one extra idea. And what does this all of this give me? An extremely dense microstructure. So after hydration for about 28 days, now your structure is looking like this. And you will know, anybody who has seen an electron micrograph will know that the extremely bright particles that you see are the unhydrated cement particles. So an immediate question is that, well, I bought the most expensive component that I use in concrete, and you're using none of that. See that? My cement is not being hydrated. I'm just leaving it unhydrated. That is a trade-off that you will have to live with in this, because if the cements start to hydrate, you can remember your basic cement class. When the cement hydrates, it increases to twice its volume. When the same mass increases to twice its volume, the porosity has to increase, right? Therefore, if the cement hydrates more and more, the hydration products are more porous than the cement itself, which means the structure is going to be less strong. So I will need a few unhydrated cement, but then the remaining parts to be filled with all of my other materials. And in this picture, bottom, the colored picture, what you're seeing is, where is all my calcium? The green is all my calcium spread around. The purple is all my alumina. The red is all my silica that is spread around. So I see where all my different chemical compositions are. And I want to show you this picture also once more, just to look at. Typically, you get a CSH gel, calcium silicate hydrate gel, when you react cement. That calcium hydrate gel has a stiffness of about 25 to 30 gigapascal. It's somewhere here. But the hydration product that you form from the UHPC mix has about a 50 gigapascal stiffness, which means you have made the whole matrix much, much more stronger. That is the entire idea. And then if you look at hydration, heat release, this is for a conventional concrete. All the UHPCs have lower heat release, basically because I have lower amount of water available for reaction, and therefore there is not much of reaction happening, which I see in this microstructure with a lot of unhydrated cement particles, a trade-off that I'm willing to live with. Okay, so let's go to a few different common UHPC mixtures. This is what you see. Generally, cement, sand, silica fume, quartz, superplasticizer, steel fibers, water, pretty much the same thing everywhere. It's all sand, sand, sand. Nobody really uses coarse aggregates. I'll tell you a way to use coarse aggregates also. So how would we do a rational material design? So I'll do another 5 or 6 slides and stop for a couple of minutes if you have questions. So the first thing, did you say something?
No, yeah, please go ahead.
Okay. So the first process is to select the binder. I need to select my binder, which is my paste matrix, and then I have to select my aggregate. So I'll show you 2 different ways. So here is how we do the paste design. So cement, slag, fly ash, silica fume, limestone. You do a packing model. So we do it from a microstructure point of view so that we don't have to do a million different experiments. So we try to pack all these in the computer, in a computer model. You pack all these, and this tells me what proportions of these materials will give me a better packing. And then I'll do some workability studies on that, mini slump cone, etc., etc. And then I will choose what my paste has to be. Similarly, I will use an aggregate packing model. So I have, in the US, we call number 4, number 8, number 10. Number 4 is maximum nominal size of 4.75 millimeters. This is 2.36. This is 1.18. So basically, my aggregates are 4.75, passing 9.36 mm, retained on 4.75. That's my maximum size. And then you do the dry rotted unit weight of that aggregate, and you do a mathematical model for that aggregate to see what is the best combination of different materials that I can get in the aggregate. Then here is a model that I showed. You do that, and then I do a bunch of different paste matrices with different amounts of fly ash, slag, metakaolin, silica fume, limestone, all of that. I do a lot of rheology. You don't have to do all of these. It's just showing how we get this. But then we select a few combinations and we get compressive strengths of 150 to 160 megapascal. That's what we wanted. And you will choose the mixes that you get, give you these mixes. At 90 days, you will get as high as 170 to 180 megapascal because you have a lot of fly ash in this which will react, or slag which will react at later ages. Aggregate packing is challenging. Aggregates are irregularly shaped. You cannot place the aggregates one by one. So you have to figure out some way of doing a packing density. So if I mix 30% of this with 20% of this with 20% of this with 30% of this, will that give me a certain higher packing? So again, the quest is optimization. So we again do a computer model here. We split the aggregates into different sizes. We find the dry rotted unit weight of each of that, and we do a computer model and use a certain equations in the model. These are all available in the literature. You use that model, and then you use these different combinations. We have about 900 different combinations of aggregates that we try to see which one will give me the densest possible packing. So how much of these different classes of aggregates will give me the densest possible packing? The idea again here is you pack the aggregate to the densest possible fashion. You pack the cement paste to the densest possible fashion, and then you mix both, and then you stand the best chance of getting the most densely packed concrete. So very simple idea. You have two distinct components, paste and aggregate. You pack the paste well, you pack the aggregate well using scientific theories, and you mix together, you get the best concrete. Now, can I do it all trial and error? You possibly can. Instead of taking a week or 10 days to design a mix, you probably will take 6 months to design a mix because you're doing a lot of trials and you're waiting till 28 days to get the strength of each of those. So from an efficiency point of view, this is a really nice workable idea. We have made a software also to do all of these packing models together. And here is some packing fraction with different volume fraction of coarse aggregate. How much of packing will I get? So I will go and typically pick up the maximum value of this, and that will be what I will use. So 900 aggregate combinations that I talked about. And so I get a packing density of aggregates of 0.696, which means I have about 30% of remaining space within the aggregate. I fill that with a very, very dense paste. And that's the idea. And here are the optimized mixed compositions. And you have water cement ratio of 0.16 to 0.18. Superplasticizer content of 1.25% of solids by weight of binder. That translates to about 4% of polycarboxylic ester superplasticizer by mass of cement. It's quite a lot of PC admixture to use, which really influences the cost of the mixture, which I'll show you in a minute. So scaled up mixes, I'll show you a few mixes that we have done. Here are the aggregates that we are mixing. And the mixing process also is much longer because you have to disperse all these particles really well. Aggregates in the saturated surface dry condition, add some amount of water, fine aggregates added, microsilica is added so that silica fume gets really distributed nicely. You add limestone again, then cement. So you add the finer to the coarser in that sequence. And then you mix all the blends. You add the first 1/3 of water superplasticizer, you mix. Second 1/3 of water and superplasticizer, you mix. And then finally, you get a really nice cohesive mix, as you see here. And finally, you add the fibers, steel fibers to the mix. And then this is how it is. A really nice mixture, doesn't segregate, doesn't bleed, very high flow. And remember, this is a 0.18 0.16 to 0.18 water cement ratio mixture and see how nicely it flows. And this has about 3% by volume of fibers, steel fibers, lots of steel fibers in this mix. You need long mixing times, intense mixing. So you cannot do your drum mix and all. You need a very high shear mixer like the one that is shown here. Ready mix truck will work really well because you can control the number of revolutions of the drum to change the shear rates. So I will stop here before I go to properties of UHPC if you have some questions.
Yeah, Professor, if you go to the Q&A tab,
Okay.
the questions are raised one by one. You can answer.
One by one, I
take
can
two,
answer.
three.
So here's what I would suggest, Professor. We have each of the questions and we are following those as you take them up. Why don't I pose the question to you and you can decide how you want to take this forward, whether you want to type the answer or you want to take this live, right?
Okay, okay. I mean, some of these questions can be very quickly answered. So let me see if I can answer the quick ones first.
Sure.
Okay. What is the minimum water cement ratio, water binder ratio we can reduce and take care of autogenous shrinkage cracking in concrete? Very good question. Autogenous shrinkage cracking will be a problem. 0.16 to 0.18, definitely you'll have issues with autogenous shrinkage cracking. Therefore, curing of UHPC is of utmost importance, and you should not let down on the curing practices. What's the role of reactive powder? Reactive powders will react with the calcium hydroxide formed from cement hydration to give you secondary CSH. I will show that a little later. What may be service life of UHPC? I have seen numbers up to 100, 150 years, but since we don't have that for that long, we don't know what it is yet. Testing size of cube for UHPC. You can afford to use slightly smaller cylinders or cubes because you're testing mortars, essentially mortars, not concrete. So there is a standard, there's an ASTM standard that's out there. Now I forgot the number, but you can look at that. Durability, we'll get there. Feasible to use UHPC in a high-rise residential project? Absolutely, it is. I'll show you some design scenarios as we go later. It seems the rate of hydration will be higher than any other concrete. Requires a lot of curing. Absolutely, yes, it requires a lot of curing. People started using GGB as a manufactured stand. Sometimes code is allowing, good to use from durability point of view. I really don't know about manufactured sand, but I have seen it a lot being used. But if that's the only available material, you have no choice. You have to use it, right? Which software can be used? Check the particle packing of concrete. There are a few softwares available. Many of them are proprietary. We develop all on our own. So, and there are different research papers that are available that you can go in and look at software. But there is no one software that I would recommend. Codal recommendations used for design UHPC. It's still a work in progress. We don't have a lot of codes that have been developed. Whatever codes are there are for infrastructure, bridges and bridge connections. Can you mail the presentation of webinar? That's a question for Priyanka, not for me. What's the length of steel fibers used in UHPC? Typically, 1/2 inch is what we generally use, but you can go lower also. Which software packing is done? We talked about that. Durability tests. In the case of blast-resistant concrete, will the percent of fiber remain 1 or 3? It depends. Again, it's a design question. 3% will give you good ductility. Anything more than 3, you will have a very difficult time mixing that concrete. So that's a thing that you have to consider. Concrete of fiber means how can it flow? I showed you how it flows. You can design the mix really well. 1/2 inch, it flows wonderfully well. Doesn't this mixing have low water binder ratio make the mix more sticky? Yes, mix will be more sticky, and that's where admixtures come in.
Yeah, Professor, we'll go back to the presentation.
Okay.
Some of the questions we can take in the end because it's the more than 30 questions are there.
Okay, we will go at the end. I was hoping for a breather. You are not giving me that. Okay, let's go back. Can you get my slides back up, or are they there already?
Yeah, the Priyanka will share.
You'll have to start. You have to start sharing from.
Oh, I have to start sharing again. Okay. Right. Good. You can see now, right?
Yeah, perfect.
Perfect. Okay. So let me get my pointer spotlight. So let's talk about properties. So we've done a very quick, I've done this in 35 minutes of how to prepare a UHPC mix. And then now the next question is, oops, why is it not? Okay, so compressive strength. Everybody likes this. Everybody likes the idea of compressive strength. So compressive strength is typically done in cylinders in the US. You guys use cubes, it doesn't really matter. And we used 2x4 cylindrical specimens, two reasons. We have a very high fidelity testing machine, but it doesn't have an extremely high capacity. So if I use my 3x6 cylinder as it is, I cannot get the entire strains. But a 2x4 cylinder is good for me for multiple reasons. One, my maximum particle size is only 4.75 millimeters, whereas with 2 inches, I get 50 mm. So I have 10 times the size of aggregate as the dimension of my cylinder, which is good. So we did 2x4. We have done a few 3x6 cylinders also. Really doesn't make that much of a difference. The thing to note is contrary to conventional concretes, your surface preparation for UHPC testing has to be really, really, really good. It has to be really smooth so that your surface roughness is very low, because even if there are slight unevenness on the surface, you will have stress concentrations, you will get much lower strengths than you would actually want. So you may make sure that your surface is very, very smooth. So we have a load cell, we measure the axial strain, we measure the radial strain. I'll show you in the next slide. Okay. Suddenly that is not showing up. Oops. Okay. So, compressive response. So what you're seeing on this figure is the strength or stress plotted as a function of axial strain and radial strain. If you remember your first year, second year engineering class, the ratio of radial strain to your axial strain is your Poisson's ratio, and we need Poisson's ratio in structural design. So you see here, this is plain non-fiber reinforced UHPC. So you will see an axial strain of 0.3%. And if you remember your reinforced concrete design, 0.003 is the maximum strain in concrete that you take for design. So that hasn't changed at all. And then you can see the radial strain here. You see the strength of all those different mixes. This F mix is the one with fly ash. M is with microsilica and limestone. And you can see a couple of things which I did not mention earlier. This first mix, 17.5 plus 7.5 plus 5. So that's 30% replacement of cement, fly ash, silica fume, and limestone. And the third and fourth mixes are microsilica, silica fume, and limestone. 20% silica fume, a lot of silica fume, and 30% of limestone, and which means this has a 50% cement replacement level. So these two are 30% cement replacement level, and these two are 50% cement replacement level. And I missed one thing earlier. I told you why we use limestone, especially when you have materials like fly ash, which has alumina in it. Limestone has the capacity to react with alumina from fly ash or slag to form what we call carboaluminates. That'll give you some additional strength. So rather than putting in quartz powder, which will just stay there, limestone powder, fine limestone powder will give you some additional strength enhancement. We need all the possible sources of strength that we need. We don't want to miss out on anything because you are targeting an extremely high strength. Oops. So again, stress strain response and compression. The first picture is for a plain mix. You can see the axes are different between 1 and 2. So maximum strain, you can go only up to 0.4. Whereas see what happens when I put in a 1% of fiber? My strain capacity increases, my capacity to deform, my capacity to carry a lot more tensile stresses even after cracking, even after the peak load increases. So that's where the fibers come in. So from here, you have no more strength after you get here. But for these mixes, even after you reach your peak, you have some amount of residual strength. So that's the important thing with fibers. And when you get to 3% fibers, the black line here, the peak is roughly the same, but look at the ductility. More fibers makes your concrete more ductile. So that's one thing to note. Again, one more same picture showing all those together. So the red line is no fibers, axial and radial, and the black line is with 1% fiber. This dotted line is with 3% fiber. So you can see that with 3% fiber, you have an extremely high strain capacity, which means, just to give you a simple example, if I take it to 0.4% strain, for my UHPC mix with fibers, I still have 100 megapascal of stress left, even after cracking. You see that? And I'll show you some more pictures as we go through. You've cracked here. This is your peak strength. But even after cracking, even when your strain has gone up to 0.4, 0.5, you still have 60, 70, 80 megapascal of strength left in the system. That is what we call the residual strength, the strength post cracking, which means even after cracking, the structure still can carry some load. In unreinforced concrete, this will not happen. In plain steel reinforced concrete, steel bar reinforced concrete, this will happen. Steel will take some of it, but then steel is not distributed as uniformly as in fiber reinforced concrete. So you will not have that much of an effect. Flexural strength. So this is important. So if you're building a beam, if you're building a bridge, we need bending strength, flexural strength much more. You can see about 20, 25 megapascal flexural strength with 3% fibers, extremely high flexural strength, right? Your M25, M30 concrete typically has a flexural strength of 4 or 5 megapascal. Here you're talking about 25 megapascals. So extremely high flexural strengths. And what does the fibers do? That's just a picture of what you are doing. You can see that fibers are holding the structure together. Fibers are bridging a lot of cracks and they're holding together. And by the time you mix it and create it, you have fibers in all random directions. So cracking is controlled in all possible directions. Let me show you one picture of how cracking happens in this mix. So you can look at this carefully and you will see here. So what you're seeing is I'm loading this beam and you can see the cracks starting to form. You can see multiple cracks starting to form here, right? 1, 2, 3, 4 cracks starting to form and then there's one dominant crack that goes all the way through and fails a specimen. You see here, extremely high strain at the tip of the crack, and all this red color means very high strains, and then finally it is cracked. So you see a crack forming here, you saw a crack forming here, a crack forming here, a crack forming here. Now that is one of the very, very, very important attributes when you're using this material for infrastructural applications or very high-rise building applications where there is extreme amounts of load. What you're seeing now is one crack that can go in and completely fail a conventional concrete is not going to be the case here. The stress is dissipated by multiple cracking. And that is the effect of fibers. Fibers enable multiple cracking to happen, and that multiple cracking releases the stress. Your structure can carry load even after the peak load has been reached. So this is something that is quite an important idea when you want to design with this material. So therefore, the key idea is your conventional reinforced concrete design where you ignore any tensile contribution from concrete is not going to work. So if you're designing a multi-story high-rise structure and you want to design the beams with ultra-high performance concrete, you cannot use conventional design procedures because your conventional design procedure will give you no benefit in terms of load carrying capacity because you're ignoring the tensile contribution of concrete, whereas you're now seeing tremendous effect of this multiple cracking where concrete can have much more tensile strength. So I'll show you a little bit later that idea. Now, again, the same idea of load deflection response. That's 1% fiber, that's 3% fiber. And you can see here maximum deflection, say the point D has a maximum deflection here of 3 millimeters, whereas the corresponding point D with the maximum strain has a 2 millimeter deflection. So with increasing fibers, you get much more deflection. you see much more cracking, random distributed cracking also that is formed. So all of these are very useful in developing procedures on how we can do design with ultra high performance concrete. The point that I want to make is, if you just make ultra high performance concrete in your ready mix plant, you will have nobody buying it unless somebody knows how to design with this concrete. If you are designing a 150 megapascal concrete and using your conventional IS 456 rules to design a reinforced concrete structure, you're not using the effective properties of this material. So all of these tests are showing you that you need to make sure that there are newer design standards, and some of them are coming up and it will take time. So you have to start with fewer applications, infrastructure applications, bridges where there are standards already coming out, but then you can transfer those to high-rise structures also. And here is a stress crack width relationship. This is basically a stress versus the width of the crack. Here there is no crack at all. I have a tensile stress of about 4 or 5 megapascal with 3% fibers. I have a tensile stress of 8 or 9 megapascal. And with increasing crack width, I can see my stress dropping. But look, even when the crack width is 2 millimeters, I still have a 5 megapascal tensile strength. And 2 millimeter crack is a big crack, right? For anybody who looks at concrete structure, a 2 millimeter wide crack is a really, really big crack. Even with that 2 millimeter crack, look, I have tremendous amount of load carrying capacity, which means your structure can be designed in a much more ductile regime. Your structure can be designed for a lot more of ductility than you traditionally use it for. So that is again another way of showing it. Now, for those of you interested in durability, it's a, I really wouldn't do these tests and waste a lot of time, your rapid chloride permeability test and all of that. If you get 150 megapascal and if you have only used a water cement ratio of 0.18 and you got a self-consolidating concrete that filled the mold well, that filled the structure well, it's going to be very good. So you look at the RCP values, 238, 365, very, very low Coulomb values. Okay, and this is 28-day values, and I don't have 90. I mean, I have not shown 90-day values. At 90-day, this mix with fly ash and silica fume went down to 85. Really, really low, almost no chloride permeability if you're using a rapid chloride permeability test. Now, I'll be very careful with the use of RCPT. I don't like that test, but it's a standard and people use a lot of it. I like the diffusion coefficient test better. And you can see in the diffusion coefficient test also, you are an order of magnitude lower in the diffusion coefficient, non-steady state migration. So chloride migration, chloride permeability, very, very good. The reason for that, obviously, the microstructure is much more dense. The porosity is lower. So this is mercury intrusion porosimetry. So that's not a real good representation of porosity because it gives you the pore, all the pore sizes, the ones that are useful, useless, all of that. But you can see the porosities are lower. But what is important is the blue bars, the pore sizes. The size of the voids, the size of the pores are much, much lower in UHPC. And it's important to note that it is the pore sizes that dominate your durability than the porosity. Porosity is very important, but pore sizes, how large your pores are, typically dominate your durability much more than your porosity. And you can see that in all of those. And one more thing that you can look at, calcium hydroxide content. You can see with all the UHPCs, which I'm showing here, the calcium hydroxide content is much lower than the high performance concrete or the control mix. The reason being that with time, you will have it at 28 days, you will have much lower calcium hydroxide content because the fly ash and silica fume are reacting. At 90 days, the values are even low. So calcium hydroxide, which you really don't want in concretes, are also gone. Sorption, if you want to look at moist water absorption, same idea. Porosity and pore size are much lower. You can see the secondary sorptivity, which is a long-term sorption, long-term water absorption. That value also is much, much lower. The initial values are high because that's a surface effect on how you have cut and treated the surface. But the secondary values, the secondary sorptivity values are much lower. Okay, so finally I'll take probably 5 minutes and do and show you what we want in flexural design. So if you have a UHPC section without any steel reinforcement. So if you look at a section without any steel reinforcement, all you have is steel fiber. This is your strain diagram. Ultimate compressive strain of concrete 0.003. That's your tensile strain in steel. That's your neutral axis if you're designing a beam. And typically your concrete contribution ends there. And below that, I consider only the presence of steel. But since I have a fiber effect, which I showed you earlier, I can take quite a bit of tensile stresses. That red zone is the tension that the fibers can take. Now throw in steel rebars like you would do for a regular beam, and then that's a strain in steel. You get a certain tensile force because of steel. There's a certain tensile force because of fiber. There's a compressive force because of concrete. Now, if I take the moments of all of those, my moment capacity of this beam is going to be much higher because its fibers contribute to a significant amount of tensile force. So I get now much more improved contribution. So this entire zone below the neutral axis that would have otherwise been wasted is now being efficiently utilized with steel fiber. And that is where design will have to come in along with developing a material, new material, in order to get the complete benefit of this material. Otherwise, we will do a compressive strength test, tell everybody that I have 180 megapascal concrete. In actual design, that will not show up at all. So these added advantages should also come in to make the best use of these materials in design. I'll skip this. Let me go to the cost. So this is all US numbers. So other countries could be different, but per cubic yard, which is what point, I said somewhere earlier, what about a cubic yard to cubic meter conversion, but whatever that number is, per cubic yard, it's about $2,000 for a proprietary UHPC. So if I have to buy a UHPC from a company that sells UHPC, that's $2,000 a cubic yard. Just to give you a point of reference, a conventional concrete, if I want a 30, 40 megapascal concrete from a ready-mix plant, I pay $150 maximum. Okay, so I'm talking about 15 times the cost for UHPC. So ordinary concrete is $109, $110, $100, depending on the cost, on the mix. But here are the mixes that we have done that gives you the same performance as these. Microsilicon limestone, 50% cement replacement, 30% cement replacement with fibers, with 3% fiber. So fibers add a lot of cost. What is the cost per KSI? KSI is kips per square inches. So if I need 100 KSI, which is 100,000 PSI, about $84 for proprietary, or $43 for my design mix. And you see the relative cost here. Steel fibers or super plasticizers. If you don't have fibers, super plasticizer becomes the most expensive one. If you have fibers, then fibers become the most expensive component. So per cubic yard of concrete, so that is super plasticizer, that's fiber. If you don't have fibers, that's what it is. So fibers and super plasticizers or admixtures take a significant amount of cost in these mixes. And that is why optimizing the cost is very important. Optimizing the design is very important. The ones that I showed, are they the best optimized designs? Probably not, but they're fairly close. And optimization depends on what materials are locally available, what materials have the best performance when you have them locally available. So that's something that that you guys can do it based on what is available. But again, the idea was to show you a methodology, show you a variety of applications that you can start using this material for, and hopefully develop newer designs and newer approaches with it. So I will end up with a final slide. You can use a multi-level particle packing approach. You can put all these particles together, get very high compressive strengths, very high flexural strength, high ductility, high durability. One thing that needs to be noted is a random trial and error process will not work for this this set of mixes, because you have to control the microstructure very, very well, because even a slight flaw, a slight defect can cause dramatic reductions in strength. If you carefully design the material using a lot of local materials, you should be able to reduce the cost. And then the idea that you might need better models, better design standards, better codes, but that's always a work in progress. I just want to throw out something that is new, that is upcoming, so that you can think about this and think about some of the applications. And if you have a ready mix planned under your disposal, if you have a laboratory that you can definitely try these mixes out, and see what kind of value addition that you can give to your customers, what kind of new strategies that you can do. One very simple idea is that you can reduce the size of columns and size of beams because you're having very high strength. Even you can use conventional reinforcement, conventional longitudinal reinforcement in columns, conventional reinforcement in beams, but you can reduce the size of beams in columns because your concrete is very strong. So those kinds of changes can also be made. So I'll stop here. Thank you very much. And I'll let Manikandan tell me what I should do next.
Thank you, Professor. We will move to the Q&A. Priya,
Okay.
is it okay that we will take up the questions?
Yes, please. We have tons of questions with us. We have, apart from the ones that you already answered, Professor, we have over 50 questions. So I do encourage Professor Dr. Manikandan to take those questions up with you. You'll probably be able to take a few questions, but a majority of these, I invite you, audience, to please go into the Concrete Club app. And shortly after the question answer session, we'll tell you a little bit more about it before we close up, before we wind up this session. So Professor Manikandan, please take over with the questions.
Okay.
Professor, we go to the Q&A tab.
Okay.
You can see the question. The first question, shall we use glass powder in UHPC? From
Absolutely.
that, we will start the...
Absolutely, you can use glass powder in UHPC. The only thing that you have to be very careful when you use glass powder is the fact that glass powder in concrete is a large function of the size of the glass powder. So if you have not ground the glass powder really, really fine, you are exposing your concrete to potential alkali silica reaction. So that has to be carefully taken care of. But if you have a very finely ground glass powder, you should be good. Water curing compound. I do not know the type of curing compounds available, but if you are using a curing compound, that is fine. But ultra high performance concretes are very, very sensitive to autogenous shrinkage. So be very careful. And we always recommend that at least for the first 48 hours, you use water curing. Is it possible to use brick waste to produce UHPC? Maybe if you crush bricks so nicely and make it a fine ground powder, you might be. But for a material that has to give you 150 megapascal, I wouldn't take that risk. Recommended days of curing and curing practice. Again, 7 to 14 days in conventional concrete is a recommended practice. I don't know who recommended that. If I have unlimited time, I will cure my concrete for unlimited time. Right? So you really don't have to worry about how much time you have to cure it. You have to cure it as long as you have to get your properties done. Blast resistance will have more fiber. You might need more fiber. I talked about that. Some of these questions I already answered. These are all questions from... What curing methods shall be followed if you want to achieve compressive strengths beyond 180 megapascal? You might have to do steam curing or high temperature curing. You cannot do that in field, but you can definitely do it in a precast concrete plant. And there are precast concrete plants that do high temperature curing and get up to 200, 220 megapascal strength. Can you explain whether self-compatibility is also assessed with the optimized aggregate? Yeah, optimized aggregate volumes can give you the optimized paste content. But again, it is subject to you doing experiments because every model or most models assume spherical aggregates, and you don't have spherical aggregates, right? So you probably will have to test them out and validate it. How are fibers accommodated in particle packing? You can do that. There are wonderful ways of accommodating fibers in particle packing. So basically if you throw in a fiber in a particle mix, the fiber will space the particles away. It will increase slightly the porosity, and you can account for that with a slightly higher amount of paste. What amount of calcium hydroxide in this concrete? Calcium hydroxide essentially is a function of how much cement has hydrated. And since my degree of hydration of cement is 0.25, 0.3 max, my calcium hydroxide content also is going to be very low. And therefore, you will have, so the question is that if the calcium hydroxide is low, what will happen to durability? Corrosion guys, I know it's a corrosion question, and corrosion guys would love that question. And I'll tell you, the competition between an extremely dense microstructure or leaving some amount of calcium hydroxide, always microstructure wins. No matter what else you do, if I can control my microstructure and permeability so well, I don't care even if I don't have any calcium hydroxide. I will still be able to control the penetration of chloride ions, and I'll still be able to keep the steel protected. At what age strength increment becomes nearly constant? That's a big function of how much you cure, especially when you have materials like fly ash and microsilica and all of that. So if you cure for 28 days, cure for 90 days, your strength will still go up till 90 days. A topic of Ferroc, which is a potential alternative to conventional cement. Ferroc is not an alternative to conventional cement. I did work with Ferroc. I was one of the inventors of Ferroc. It is not an alternative to conventional cement. It is a very specialized material with special applications, but it will give you phenomenal amount of tensile strength. Specification of steel fibers. You go to any steel fiber manufacturer, whoever is manufacturing, they'll give you the best steel fibers, because steel has to be steel. It has to have 210 gigapascal elastic modulus. There is nothing else. And then it's only the size that matters. Can we use UHPC in underwater construction? There are companies that are making piles with UHPC and drilling those piles for offshore oil platforms and wind tunnels in the lakes and in the ocean. So yes, it can go inside water really, really well. A size of particles is lesser, surface area is more, requires more water. As a water wind ratio is less, how will it be managed? That's what I showed you with a lot of admixtures. That is the only way you can manage the lower amount of water. What is the retention period of UHPC? Again, depends on the admixture type that you use, depends on a lot of other things. Aspect ratio with respect to fibers, it is an inch, so what, half an inch, so 12.5 millimeter fibers, and I think the diameter of fibers was 1/10 of a millimeter or so, or 1/20th of a millimeter. I don't remember the number. Is it possible to design UHPC using GBG waste or fly ash as binder in place of cement? You cannot replace cement entirely, because then Manikandan would not do this talk. You cannot replace cement entirely. You still need cement. You need about 50% of cement at least, because the early strength comes from cement. Fly ash and GGBS are wonderful. Now, you can ask me, can I make a UHPC geopolymer? I would say yes, go ahead and try that. You can do that, but then it's going to be a little more difficult. Cement is your best material that gives you a lot of control, and cement masks the problem with a lot of other cement replacement materials that you use. And now, do I say that cement is the best? Probably not, but it masks a lot of problems with other materials. How high strength concrete can help to small buildings and individual residential buildings? No, if you're using it for 3-story buildings, you're wasting a lot of money. Don't even bother. If you're not doing more than 10, 15, 20 stories, don't even go near it, because you're just spending money. What admixture may be used to reduce cohesiveness, stickiness of UHPC? Tell the principles of working of these admixtures. Principle of working of these admixtures you can see in any standard concrete textbook. So I don't want to spend time talking about that here. And any admixture that you use here is going to be a very high range superplasticizer polycarboxylic ester type admixture. I will not name names here, because then I would be taking sides of an admixture manufacturer, which I do not want. but every admixture company now manufactures a PC admixture. How to avoid air entry due to high SP addition? Lots of mixing and lots of vibration. Can't do much about that. How increasing the cement amount causes decreasing compressive strength of ultra high performance concrete? Well, I did not say increasing cement causes decreasing compressive strength. Increasing cement will just make you waste a lot of money because that cement is not hydrating. So optimization means you just find out how much cement you would need and leave it there. Range of modulus of elasticity. If you do not have fibers, your modulus of elasticity is still in the 40, 50 gigapascal range. If you put in fibers, you can have higher stiffness. How to optimize the fiber content? Trial mixes are the best way of doing it. Instead of straight fibers, you can use 5D fibers, you can do crimped fibers, you can use hooked fibers, you can use all of that. Repairing conventional bridge with UHPC, compatibility check. Absolutely, any repair, you have to do compatibility check. Again, if you are repairing a bridge that was built in 1970 with a 30 megapascal concrete, and suddenly you're going to put in 150 megapascal concrete over the 30 megapascal concrete, both of them are not going to shrink together. Volume changes are going to be different, so you have to be very careful. The bonding agents that you use, the relative deformations that you look at has to be different.
Professor, there is one more.
Yeah.
Professor, there is one more question. Do you think of the first one, the alkali resistant glass fiber in place of steel fiber?
Yeah, you can use alkali resistant glass. AR glass fiber is possible. Yes. Yes. How can we understand the complete procedure of preparing UHPC in a site? There is no book as yet, but you can get a lot of research papers. You can search for a lot of research papers. Actually, the best source of information is Federal Highway Administration of US. You can go to fhwa.org, and they have plenty of information on UHPC, free information that you can download, and it tells a lot of different things. So you can do that. Viscosity modifying admixture, it depends. Again, with more and more admixtures, I always tell my students, I always tell clients who come to me this, if you ask me, do you use this particular type of admixture? It is like asking me what type of spice do I like in my food, right? Somebody might like high spices, somebody might like it bland. Whether you want viscosity modifier or not is depending on your taste and the type of concrete that you get. So there's no easy answer that we have. What is the effect of very small pore microstructure on shrinkage? Good question. When you have the pore sizes that are smaller and smaller, your shrinkage is going to be large. I'm not worried about shrinkage as such. I'm worried about the cracking that comes along with shrinkage. And that's precisely my point, that you should cure UHPC is much, much, much more than you use your conventional concrete.
One last question, Professor.
What is that?
Maybe one last question, and then
okay.
We can request everybody to engage with you over the Concrete Club app itself.
Okay.
So let's do the last.
Yeah, I'll do this one last question. Calcium hydroxide is low. What could be the effect on carbonation? Carbonation reduce strength and induce shrinkage. Good question. If the calcium hydroxide content is low, you will have carbonation. But again, remember, carbon dioxide also has to diffuse through the concrete. If you make a really, really dense microstructure and make diffusion much slower, CO2 also has no way to go. So again, I keep telling this point all the time. For UHPC, microstructure is the key. You get it as dense as you possibly can. A lot of problems will go away.
Super. Thank you so much, Professor Narayanan. And while we still have your attention, you've done a really quick fire round with all the questions. We got almost 100 questions in all. And clearly that shows how interested all of the participants have been and how engaged they've been throughout this long but extremely interesting and engaging session. I would like to take a few moments over here and introduce to our audience and to you this idea of what we mean by the Concrete Club. The Concrete Club is not a new initiative by us, but it's something that we have been shaping up and building over especially the last year, where one of the first things we're doing, and you see on your screen at this point of time, is the ability for practicing engineers, practicing architects to be able to build and share their own portfolio to talk about the work they've been doing through this app itself. And you can share it socially, you can share it through prospective clients. For those of you who are in fact practicing professionals. This is a screen over here. You see a lot of us who are working with design or who are working with creating existing structures do want to get inspired. We do want to get ideas of what's happening across the world, what's happening in our markets. So we invite you to participate widely in the Inspiration Zone. The Inspiration Zone is essentially your own Instagram. Projects and things that you find inspiring across the world. Share the photographs. Talk to us about why it's inspiring for you, and what might others learn from this. And remember, all of this we're trying to do is in service of better building practices for us and for our future generations. What are the lessons you find are the better building lessons? Are they about better design? Are they about better product quality? Or are they about better sustainability? And I leave that up to you and to share with your colleagues over here. What is it that you find inspiring, really, and how can you share that story? This is the section that we really want you to utilize. Each of these knowledge series that we have, we do know that we are short of time. So we invite you to share all of your questions in this section. And of course, we invite you, Professor Narayanan. You've been very kind and very patient throughout this section, but we also invite you to participate in this discussion section. And also, call your colleagues, share the knowledge that you have, use this as a fora for your expert platform. And that, once again, wraps up our session for the day. I leave you with thoughts on what else ACC has been doing. We are, of course, a part of the ICJ Online, the Indian Concrete Journal, which has been publishing research papers from several different technologists, researchers, and practicing experts across the country. We have been taking this time and utilizing this to make it more meaningful for some of you who are practicing and looking at perhaps case studies. So what you see in the bottom half left side corner is case studies that we've pulled together of practicing architects and practicing engineers with case studies of some of the work that they've done. We invite you to not just review these, but also bring your own contributions and share with us what you think brings out the best of these case studies. With that, I hand over to you, Professor Manikandan, to thank the professor and the audience over here. We have shared with you what we believe is the first in our knowledge series of good building practices. And we are glad that all of you could join us. We hope that you enjoyed this session. Professor Manikandan, please.
Thank you, Priyanka. Professor, we, on behalf of ACC, we thank you for spending your valuable time in the late evening. And you have shared, your presentation was really interesting to us. And most of the participants will gain some knowledge, particularly these ready-mix concrete manufacturers. And of course, the consultant, because you have thrown the light on how to design this ultra-high performance concrete. It's not like a conventional concrete design. And even if you want to use this product, it needs some designs procedure to be followed to make use of this product more effectively. And it is very well explained that how we can reduce the concrete consumption in terms of sustainability point of view, as well as how we can make use of this material more effectively in terms of designing more slender structure as well. Thank you, Professor. Thank you once again on behalf of ACC. I thank all the participants and also my co-host, Mrs. Priyanka. Thank you so much.
Thank you.
Thank you.
Thanks.
Thank you.